talk a little bit about brain-machine interfaces, what they are, and this slide is from a talk. Actually, I repurposed some slides, and this is a little older, and that title was tongue-in-cheek, what they are and how they will affect you, the future, and everything. It's about 3 years old, except that the title now is not even funny, and it's true. So they will affect you, they will affect all of society, they will affect the future. In fact, they're going to affect everything. It's a very interesting turn in technology and in society that's happening. I didn't say who I was, by the way. My name is Regina Monaco, and I have a company called the Center for Dynamical System Studies, and I study dynamical systems. The brain is one of them. Okay, so I heard a noise. I don't know if that was a question, but I will continue. Questions should come at the end because everybody's mic, as I understand, is muted. So today I'm gonna, there's a little outline here. This is gonna be an overview, what are brain-machine interfaces, give a brief description, how do they work, what are they used for, what's the difference between a non-invasive and an invasive BMI system, what has Musk done in Neuralink. That's gonna be sort of woven into the talk and commentary. And people also are really focused on Neuralink right now. Everybody's talking about Neuralink. It's in the news. It's all over YouTube. His commentaries on his commentaries. But there are companies that are doing similar research. And I just picked two because I think they're very equal in size to Neuralink. In fact, BlackRock Neurotech, I think, exceeds in many ways what Neuralink is doing, and I don't hear a lot of talk about it. So BlackRock is the company that put Neuralace out, and that was in the news. They've also been working with something called a Utah array. There's going to be a picture of that coming up. They've been around since 2008, I believe. They have millions and millions of dollars of funding. They have multiple FDA approvals. And what I think is the most important thing that they have is they're able to collect signals from a single neuron, which a lot of BMI and the technology is not able to do. They've also designed a variety of different electrodes. Electrodes have physical limitations. They can collect different qualities of signal. So that's actually a weird noise. I don't know if anyone else hears it, Brian. So if you could mute it or something. Do you hear that? So brain-machine interface, I think I started to say, they've actually been around in literature for decades. It's surprisingly long amount of time, and they've been referred to in a number of ways. So just to collect them all together, they're sometimes called a neural control interface, or an NCI, a mind-machine interface, a direct neural interface, a neural prosthetic, or a brain-computer interface. And what the device does, no matter what you call it, it all does the same thing. It allows a direct communication pathway between the brain, which is now enhanced or wired with the device, and an external device, usually a computer. The goal is to connect the human brain to a computer to do something that neither the brain nor the device can do on its own. It's definitely an enhancement, right? And that's what it does, but that's also all it does. So it's good to have a clear idea of what these things are, because people are starting to think of them as magic. They're not magic. So this is an older slide deck, and there was something else here. So I have to apologize. I was wondering why some of the things didn't look familiar to me. So let me go back. Uh-oh, and I've lost control of, okay. So whatever this was, we had done it. Why screen? Why? Okay. No, this is really an earlier version. Okay, I'm gonna have to wing it, guys. So there's a lot of different researchers who are in this field. So like AI, well, let me back up a sentence. So in the past, if you wanted to do mathematics, you were a mathematician. And if you wanted to study, I don't know, economics, you were an economist. But nowadays, in the major fields that we talk about, they're very, very highly multidisciplinary. In fact, there would be no progress in the fields if it wasn't a variety of different researchers all bringing different disciplines to the table. So AI is one of those fields where it would never have progressed without psychology and engineering and programming. And, you know, it's a hodgepodge, linguistics, and And that's a different topic, but that's AI. So brain-machine interfaces are also in that group of things, right? You need neuroscientists, and military research is sort of at the end. You need programmers, you need Silicon Valley entrepreneurs, you need electrical engineers, you need surgeons, you need I said neuroscientists, but you also need researchers in other fields. I have medical engineers there, I don't even know what that is, but physicians of all kinds. And they're all coming to bear, and robotics, by the way, because Musk has now introduced that with the second half of his Neuralink device. The first half is the device, the second half is a robot that sews it into your brain. So all these fields are coming together, and AI scientists, I can't leave that out, in machine learning in order to decode the signals. So the field is composed of many different talents of many different people, and the learning that's been done in these fields over the past, 50 to 100 years. We have to remember that there's advances and opportunities, right? There's remarkable medical breakthroughs, but significant risks and dangers. And personally, I feel that this is an area to tread very lightly. I think in the past, for example, there was an enormous breakthrough in atomic energy, and there were nuclear bombs, and everybody took them very seriously, right? And everybody felt the heavy weight of the fact that society had designed something that could be so dangerous. We have something, I think, that these devices have the potential, not in the same way, they're going to explode in your brain, but they have the potential to reshape society in the same way, and they can be used for good or evil, and people want to use them to play games, right? It's a whole different approach. So I think that it's very important to remember, while we celebrate the breakthroughs, the medical advances, and the unbelievable entertainment that these things can provide, that we don't forget the dangers. So the biggest danger that I feel, or one of many dangers, is the existential danger to your free will, your freedom, and your privacy. This could be an enormous conversation. We're like only on the third slide. So I'm just gonna leave that for you to think about. Okay, so how does the brain give up its information? We're talking about these devices that go into the brain, and we're talking about information, but what are we exactly talking about? What kind of information is in there? It's not little gremlins that are whispering into a microphone saying your thoughts, down a telephone line to this device for somebody to listen to, right? It's obviously more serious than that. So the first thing, if you want to answer the question of how the brain gives up its information, is to define what is information. And that becomes very tricky when you talk about the brain, because a lot of people immediately go to, don't forget that your spirit and your soul lives in your brain. And I'm being a little funny. I'm not putting those people down, but you cannot also consider, while you're trying to devise or use electrical engineering, right, to figure out how these devices work, you can also worry about maybe you're in touch with God or Gaia or the universe, right, in a magical way. So putting that aside, we have to acknowledge information for what it is. Information is a physical quantity. It's always encoded in a physical substrate, in this case your brain, and it's subject to the laws of thermodynamics. So this becomes a decoding problem, and it's in the realm of engineering. That is the only kind of information that you can get from the brain, and that's the only kind of information that people in this field are interested in, nothing else. So then the second thing, now I've defined what information is let's establish, I'm sure people have a general idea of this, and some people have a really good idea of it. What is the brain made of, and how does it encode information? So it's composed of electrically active cells. Their electrical activity or signaling is what gives you the information. The cells are called neurons, and upon activation or firing, they have measurable correlated outputs. And the correlated output that is of most interest is electrical spike trains. And the electrical spike trains are caused by a change in voltage, and the voltage is what you can measure. There's other things to measure too. I don't want to, I'm sorry, I'm about to leave them out and buzz past this slide. So there's metabolic activity changes, because as the voltage changes, it has to be reset. And that's a very active biochemical process. There's magnetic signals that are tightly correlated to the electrical signals. Those can be measured too. There's chemical signals in the neurotransmitters which trigger the electrical signals. So there's like a host of changes and data that's being evinced by the brain as it goes through, the process of thinking or acting in any way. And I want you to keep that in mind, but a brain-machine interface of the kind that we're talking about, and particularly Neuralink, since that's come up so many times, is measuring electrical information. This is a cartoon of a neuron. I'm actually not going to spend that much time in it, but it's just reminding people that the structure of a neuron, here's two neurons in a row, right? And this is like from a textbook. It's got dendrites on this end, and they pick up incoming signals from a neuron that's on the other side of the dendrite. And then they jump across the synapse. So neurons are like, when you're a little kid and you have a sibling and they're teasing you and they're like, I'm not touching you, and they're bothering you, but they're not touching you. Think of that when you think of neurons, right? They never touch. They have these synapses, so they kind of are highly interlaced and tightly interconnected, but there's still a gap on the order of about 1,000th of a hair, the width of a hair, and that gap is bridged by chemical signals or neurotransmitters, and the neurotransmitter jumps the gap and makes the neuron fire, and it gives off the electrical signal that's measured by the brain-machine interfaces. So that's the point of understanding this, is knowing pretty deeply where this information is coming from. Okay, so a neuron, is a general type of elongated cell. I have no control over these slides. I just want you all to know that. Here's pictures of neurons, of elongated. Why? I hope you're laughing out there because it's amusing at this end.
Seems like a delay maybe when you're going to the next slide, probably.
Okay. Well, at my end, it's jumping around. But anyway, it's an elongated, it's not a sphere, right? It's got this general morphology that is important to its function, with spiky ends, which facilitates long distance, widespread communication throughout the brain and in fact throughout the body. Done. Now you all know what neurons are. Pictures of pretty neurons. This is actually the work of a very famous neuroscientist called Ramon E. Cajal. And if any of you are interested in this field, his name will come up over and over. He did such beautiful work that even on the order of 100 years later, people are still referring to his images. And these are some of them, different types of neurons. And the point of these slides is just to give you an appreciation of how many different kinds of neurons they are. And yet they're all neurons, right? So this is very different neurons in all these different animals, but they all have neurons. And that's why these brain-machine interfaces can be tested in pigs, or what else is he doing them in monkeys, right? Because their brains are so similar to ours, and they're composed of neurons which are electrically active, and the signaling is very similar. So this is the same question. We can say a little bit more about it. There's systems, brain-computer interfaces, mix it up a little bit, are systems that allow communication between the brain and various machines. Right now, we know that. We're experts in knowing that. 3 main steps is collecting the raw data, or the brain signals when they fire, interpreting the raw data. First, you clean it up, and you might change it from analog to digital, but basically the next step is to interpret the signal. What does it mean, right? We've got this person had a signal maybe from the back of the brain, which is the occipital region. They probably saw something. What are we going to do with that information? What is the device going to do with that information? And then after it interprets, saw something, was a cat maybe, the occipital region, output a command, pet the cat, to a connected machine or device. And the connection has to be reliable, rigorously reliable, right? You can't have the command sometimes be pet the cat and sometimes be, knock the cat off the table. That would not be a working brain-machine interface. That would be totally bad. It has to give the command according to the brain signal received, and it has to be accurate. So this technology has already been applied to a variety of problems. I have tasks here, but I would say they're problems, medical problems. Quadriparaplegics have had implants 30 years ago that enabled them to move in certain ways. Certainly 30 years ago is more limited than what you can do now. There's reduction of chronic pain. Those things are already out there. Neurofeedback helps people with meditation or biofeedback. I don't think that's the most amazing use of it, but it's certainly a common use. It can be used to restore motor function to paralyzed patients, no matter why they've been paralyzed. Communication with locked-in patients, that's really important. There's a lot more locked-in patients than you might think. There's hundreds of thousands of them. And while many surprisingly report a quality of life that's not as deeply bad as you might imagine, since I'm assuming no one here is a locked-in patient, communication would certainly enhance their ability to interact with the world and thus improve their quality of life. And they can be used, and they have been used, not can be, these are things that have been done to improve sensory processing for any. So I'm continuing the talk. It terminated at the last slide that you just saw because we had a hacker on the Meetup, and I wanted to finish the talk. We were about 6 slides in, and there's about 12 slides left. So I'm going to share the screen right now. Let's see how this goes. Share and share the slides. Current slide. Okay. I don't know what that green line is, but so we ended on this slide, and I have to remember it's like a month ago that I gave the talk. So let's see, I was describing how brain-computer interfaces work, and there's 3 main steps in that they collect the brain signals. I know to those viewing this, you just heard this, but I'm retraining. So they collect the brain signals, and they do something to interpret those signals, and then they output the commands. And interpret those signals is a small line that encompasses an entire field of engineering that includes decoding the neural code or finding a neural code. So understanding how the correlated signals in the brain work, how they come together from different areas, how they're interpreted, that's very complex. And actually the state of the technology right now is much simpler than integrating a lot of information from various parts of the brain, and it's still working very well. And I think that that's important to note that there's been some high successes even with the low technology that's being used now. It seems very futuristic, but what it's doing is actually so much simpler than what the brain is actually doing as it moves information around. But anyway, okay, so interpret those signals is 3 words, but it means a lot. And then it outputs the commands in the example I was giving to a connected machine like a robotic arm that would reliably, I think I had just said, pet the cat and not knock it off the table, or something else equally not what you intended, right? It has to interpret your neural code correctly and do what you intended. And that would be a very successful instantiation of a working brain-machine interface or brain-computer interface. And in fact, there are a number right now that are doing that. And I'll say more in a few minutes. So the commands in that output example that I just gave are currently applied to a variety of tasks, and that means the technology exists. So the reduction of chronic pain, which is not really a command, right? That's just how these devices, some devices work. They very simply emit a stimulating frequency into specific parts of motor neurons that are known to conduct chronic pain and breaking that signal. So that I'm generously folding that into the brain-machine interface definition, but some people might quibble with that. So I want to be clear on the difference. So biofeedback, people are using it for that. And I'm pretty sure I had mentioned that also. Restoring motor function to paralyzed patients, communicating with locked-in patients. And I know I had just said that there are hundreds of thousands of them, and there's a lot of people with locked-in syndrome or various forms of paraplegia, being unable to move. Which can be a subset of being a locked-in patient, and various kinds of disabilities that severely limit or ablate all ability to move. Improving sensory processing is another large field. So a brain-machine interface, actually that already exists, like a cochlear implant, which I'll mention in a few slides. So they can improve or add to, by the way, in terms of virtual reality, your senses, hearing, sight, sound, olfactory, which I'll mention, touching, and plus abilities that you don't have right now to do with just your mind, right? Texting you do with your fingers. You won't need to do that in the future. This already exists. There's a bit rate, I don't remember it offhand, that Neuralink can send text just from your thoughts, and the bit rate is higher than the previous lab group that had been working on it. So it's not even brand new or on the table. That's been done. Gaming and accessing data, like downloading Wikipedia to your brain so that it's always available. Instead of looking it up, you just think, what's some obscure bit of knowledge that I don't have right now? Boom, it's there. And that's the dream, right? That's what we're working for. So Neurolink, here's some headlines from a site called, it's here on the bottom. Here, I'll use my cursor, here, my arrow, you see it moving. So I hope this is clear, but teslarati.com and then /tag/AI. But this is an interesting aggregator site for this kind of information. So I grabbed some headlines from that. So Neuralink's human trials will begin soon. And this was December of 2022. That means in a few months, the human trials will begin. And I believe they're slated, the surgeries, we're talking about the actual implant of a working Neuralink with 1,000 plus channels into the brain, should begin being implanted into human volunteers in May or June. So this is a slide here you can see from 2020. And the goal here, Neuralink wants to implant the system into a human by the end of 2020. They didn't quite do that, although they had it in pigs by that time. And he described at that time a small 2-millimeter incision, and you'd implant the devices under an hour and then glue it shut. And the needle was 24 microns. I believe right now they're using, it's so much better than this now. They didn't hit that goal, but they jumped away past it. So it's using, I believe, a 16 micron needle. Okay, it's thinner. You don't feel it anyway. So to an end user, that may not be a big deal, but it does make the surgery a lot less inflammatory, a lot faster, and a lot easier with less damage. So, but the important thing is that instead of a 2-millimeter keyhole, they designed the Neuralink device, which I'm sorry I don't have a picture of, to be the thickness of the skull. They're just taking out a round circle of skull, the exact size and shape of the Neuralink device, which is round like a coin. And it's got a flat tail of electrodes coming off of it. So they take that circle of skull out, they open your head, they take the skull out, they open the dura. So this is definitely an invasive surgery, just to be clear. It's not a visit to the dentist. And they implant the electrode, the robot implants the electrodes. Then instead of putting the bone back, they put the Neuralink device so it's flat, and they pull the skin back over, and maybe they use surgical glue or stitches, I don't know, but it heals, so there's no bump on your head. So it's completely self-contained, no pacemaker used for powering it. It's definitely in there, and that whole surgery is done by a robot in 15 minutes. And again, that's not a prediction. This is already being done. The robotic devices exist. So this slide is showing you what they were hoping to do, and what I just described is far past that. And then I'm describing some devices that can be connected to a Neuralink. These were not, or to any brain machine interface. Oh, I don't have control of my slides. It's still true. So there's a device that can decode the neural, or understand the neural code for olfactory inputs, and it can both detect an odor, identify it using machine learning, and it's an electronic device, right? It's picking it up. It's called an artificial nose, and then output the neural code for that to your brain. So what's the effect of this? Okay, you've got a wireless link to a nose, but it's not here. It's in France, or at the other end of a cooking video, like the Great the Great British Baking Show, and they're always doing these amazing things, and they look so great. I actually don't like to watch that show because I can taste it with my eyes, but I can't really taste it. It's very frustrating. To add to your enjoyment and frustration, now you might be able to smell it, and if you're in a virtual world, Not something I'm advocating, by the way, but this is a possibility, and you will then be able to smell the baking cakes that you, not yet, in any case, the technology doesn't yet exist for you to taste them. That might be coming. I mean, they have a nose, why not have a taste? But in any case, now you'll be able to see them and smell them, so your frustration can only increase. But the point is, we can add olfactory information, and it doesn't have to be local. This is your local sensor. These would be your sensors from far away. And you can imagine if they can do that with olfactory data, what else can they do it with, right? Then there's haptic smart suits. Right now there's something you wear, and they use, it says here, they use AI with biometrics and simulate real world environments. So what that means is, I don't know, if you're playing a game and you punch something and there'll be resistance when you hit something, that you don't have to really hit anything, but the suit will give you that resistance. And coupled with what you're seeing, it will really feel like you're tactilely, haptically in this world. So now imagine if instead of the information being mechanically in the suit, it's neurally encoded and uploaded in Neuralink. Now you don't even need the suit, and you're living in the virtual world, and all the information is coming in encoded through the Neuralink. That is a bit of a sci-fi stretch. Throughout this talk, I've been saying this isn't a dream, this is real. This is a dream. But the haptic suit these are devices that are being designed separate from virtual reality. And I keep saying Neuralink, but remember earlier in the talk, I was saying other companies are doing the same thing. So for brain machine interfaces, these can all be eventually integrated. So it's really going to be more of a system. And I do think, for good or for ill, this is in our future. So let's understand it. A really good talk was given by Lex Friedman. It's called The Future of Neuralink. This is really, I'm torturing you guys by showing this link here because you can't copy it from the slide, haha. So, but you can just Google or go to YouTube and put in The Future of Neuralink, Lex Friedman. It will pop up. He's a popular speaker. He's an MIT professor of AI. He often knows what he's talking about. In fact, interestingly, he has recently put out a call for people who would like to interview with him. And I put in an application, and possibly, I don't know, the chances are probably 1 in 1,000, but I would love to talk to him specifically about this video. But in any case, he's going to go through all these different areas that neural implants can enhance, right? Alleviating human suffering, which we've mentioned, enhancing intelligence. He thinks it can enhance consciousness. That's something I'd like to talk to him about. I'm not sure I agree. Augmented body, mind, and reality, right? That's what I just said in the referring to the last slide. Gaming, virtual reality, merging technology and biology. These are in the class of the first devices that have an interface between biology and technology, and that's really important. And then he'll talk about something called telepathy, which we can discuss in future meetings or our podcasts if there's interest. I might call it something different than telepathy, but it does mean reading others' minds at a distance. And if I have a wireless connection to you and you have the device and I have a device, and the device allows a communication channel, since tele simply means far, then there would actually be a real information channel between us. And you could call it telepathy, but I would just call it enhancements, the ability to have access to other people's thoughts. And then he talks about saving memories and how that could lead to a form of immortality. And again, that's a discussion. And it would allow us to merge with AI. I don't really know what that means because AI is actually used in the Neuralink. It's a tool. But I think what he does mean is if there's sentient AIs, this would allow us to merge with them. I think that's what he means. Maybe I'll get the chance to ask him. This is the same slide that was on the same cut, the same mini slide that I reproduced on the previous slide. So, as I alluded to, there's massive medical advances, and you can read this, and I'm going to apologize for this green line. I thought it would disappear. I don't know what it is, so I'm clearly not entirely in control of my screen or Zoom, so I apologize. But anyway, chronic pain, chronic migraine, there's actually a device already on the market, and I think it's interesting. I've given talks on medical devices, and um, this particular device has electrodes that are implanted here. So there are nerves under this part. They go in through your nose. So, you really have to have a terrible condition of chronic migraine, I think, to want electrodes implanted into your body through your nose. But if you have it, I'm sure that surgery would be the least of your worries. And I do get migraines myself. I'm a migraineur, and I can tell you they're no fun. Some people get them every day. You can't do anything like that. So anyway, these electrodes are implanted, and they interrupt the flow of communication, of irritation through nerves in this region and the pain areas, the pain interpretation areas in the brain, and therefore specifically shut down chronic migraines. I think there are better medications to use, but I have to say this exists. And for some people, especially people who are refractory to medication, this is life-saving technology. And, it can address by completely different methodologies, depression, OCD disorders like anorexia, addictions, attention deficit disorder, right? All these things, OCD, PTSD, phobias, anxiety, mood disorder, because these are all, you could say, or you could interpret these all as misfirings of the brain, and they brain-machine interface would re-entrain or reintroduce healthy patterns of thinking. So not of thinking, I'm sorry, healthy patterns of firing or healthy stimulations of areas in conjunction in a correlated fashion. And I know that's a little obscure, and I'm kind of being intentionally obscure because A, these are all different. I don't know how they all work. And B, they're not really going to go in there and psychoanalyze you. If you say they'll change the way you think, that sounds like a therapist is buzzing around, physically telling you new things to think. Not how these work at all. So I just want to be clear on that. They can assist, for example, with deep brain stimulation, which is an invasive technology. They can add movement back or reduce unintentional movement like tremors and stuff in a lot of diseases, including Parkinson's and epilepsy, and all these other, and you can read this as well as I can read it to you, the damage from strokes and cerebral palsy and spinal cord injuries or breaks. And, we can go through the list. I've mentioned all of these before. They can control protective devices or wheelchairs or external assistive devices like an arm that can feed you a chocolate bar or, any number of artificial limbs that can do things for you or help you control. This is actually saying the same thing, control an exogenous limb. So the limb can be attached to you, or it can be over there, or even another part of the house, right? And you say, go get me the coffee from the kitchen and put some milk and sugar in it and then roll it into me and make sure that it stays hot and bring me this coffee that I want right now, right? So coffee sounds trivial, but you can get it to bring you medication or your EpiPen or whatever you need, medical, life, pleasure, video game, like control of exogenous limbs and devices. And then what we've already mentioned, in addition to memory loss and dementia and Alzheimer's, there's the fun stuff, right? The texting, the gaming, controlling your smartphone without touching it, interacting with the internet without touching a keyboard, communications between people, enhanced learning, enhanced memory, access to upload or download information, and helping you, of course, with all this flow of data, this deluge of data, enhancing your concentration and attention so that you can consume all this input. So I'm gonna give, oh, excuse me. 1 second, I'm making a recording. Apologies. I'm making a video. I'll be down in a few minutes. Well, I'll see if I can edit that out later, but it probably won't be worth the effort. I apologize. So here's a meandering history of brain-machine interface design. right? Galvani is a scientist in the 1780s, and he found that electricity would stimulate a dead animal leg to move. And while, of course, you could say that's not really a functional brain-machine interface, it's arguably the first human observation that electricity through an electrode can cause a biological reaction. In the 60s, there were cochlear implants which assist with hearing. Going back further in the 1930s, there was the invention of the EEG. This Professor Berger this is mostly associated with it, but also his other co-workers. And then in the 70s, the EEGs were studied continually between the 30s and the 70s, but here's a paper by Vidal et al. This is an actual name, so if you the paper, you Google this exactly and you'll find it, towards direct brain-computer communications. There it is, 1970s. There's something called ECOG, which I'll define in a slide in a few moments, but it's basically it's a semi-invasive, it's a semi-invasive, so you do open the skull and you get a device, but it sits on the brain, does not penetrate into the tissue. And those were invented in the 1940s to assist people with severe epileptic seizures. The visual neural code was studied in the 70s, decoded from the horseshoe crab eye. And I actually visited this lab. It was at Syracuse University. I believe it still is. And in that lab, they had tiny little cameras, little squares about this big, seriously, on the head of a horseshoe crab with little tiny electrodes that went into the occipital or visual portion of the brain. And then the crab would be in this natural environment, walking around with this little camera on its head. And when it saw something, its neurons, has a tiny brain. I mean, thousands of neurons, not billions, like human brains have 80 billion neurons and trillions of connections. The horseshoe crab brain, much simpler than that. So you could actually have a chance at understanding what would be encoded. And also, horseshoe crabs lead a very simple life, right? They eat, they sleep, they go towards the light to find food or mates, and they find mates, and that's it. So there's not a lot of things to decode, and that makes the system very simple. It's got a few neurons and few actions. And from that was one of the first groups to decode a neural code. And then in the next meeting, we'll be talking about hippocampal memory prosthesis. In 2020, I wrote not in human trials yet. I believe that is, in fact, I just saw a few videos. It is in human trials. And I named Dong Sung, but there's Professor Hampson and I think Ted Berger and a few other people in that lab. Don't hold me to that. You should look it up, but there's at least 4 people associated with the development of this. But the papers that I identified the most descriptive of the prosthesis was with Professor Dong Sung et al. The first brain-machine implant or brain-computer interface is recorded 1998, the Kennedy Lab. I forget what university it's at, and they also designed, in addition to implanting it and having it work, what they called a neurotrophic electrode. And the special thing about that was that it had the ability to take a signal from a single neuron, and that's astonishing. That's already 1990, and it's not already that. What I mean is it's as early as 1998. And then BrainGate came out in the 2000s, and it's a much more advanced implant that allows the user to operate external devices such as limbs. That's by the Donahue Group. So here's a big breakthrough. I just picked one of many. If you go to look up Professor Nick Ramsey at the University of Utrecht, this is directly copied from their page. Their BCI, they developed intracranial BCI concepts, right? Devices, that means for paralyzed people. Their research resulted in a worldwide first fully implanted BCI for home use. That means they don't need months of continual training on how to use it. They can use it at home, and they implanted that in a locked-in patient in 2015. So there were earlier devices, but they required an extensive hospitalized recuperation and extensive hospitalized training sessions for months before you could use them. This is a jump past that 15 years, approximately 15 years later. And that lab is developing and implementing the next generation BCI implants. And then here's a reference here, fully implanted brain computer interface in a locked-in patient with ALS, and that's 2015, the New England Journal of Medicine. So you can also look that up. You just put in this exact title and Google spit it out for you. And if you had a Neuralink, you could just think the title and boom, the paper would be right there. And then you could probably open a Bluetooth channel to your printer and have it pop out. I'm a little tongue-in-cheek, that doesn't exist yet, but I don't think it's that far away. So we're getting to the end of this. I'm going to skip a few slides. So I said a few times, and this is going to be the last section, the different types of brain-machine interfaces. There's the non-invasive, that means, and here's this picture, right? The EEG is on the outside of your skull. You can just put it on, right? Like a hat with these electrodes in it. They just sit on the outside of the skull, and they get very weakened, attenuated signal. This isn't the best example because they all look noisy and unclear, but this is the slide I have. So semi-invasive means it's placed on the surface of the brain, right? And it has names like neural dust or neural grids. And here's a picture of semi-invasive. And of course, you have to imagine that surgery's been done, right? The skin's been opened, the skull has been removed with a drill, right? The dura underneath it, which protects your brain and has 3 layers, which you can see in this picture, right? The dura, let's see, here's the dura, is brown, and then there's an arachnoid covering, and pia mater, I believe is the full name, and those are various meant to be impermeable coverings for the brain. And also the brain has a texture like jello, so these also are like wearing a girdle or something, you know, it gives it some stability. There's no bones in the brain, right? It's encased by this very tough skull, but it's like this jelly-like material, and so this dura actually gives it some structural stability on the outside. So you cut a nice hole in that and you put these devices on the surface of the brain. That's semi-invasive. And it is definitely a lighter surgery than the invasive, which is what Neuralink and other devices, some of the other devices are, not the stentrodes. Those would be semi-invasive. But anyway, and that would be a device with embedded probes. And a Utah probe I'm going to show in a slide or two. And the typical usage would be for deep brain stimulation, chronic pain, to ameliorate symptoms of neurological diseases such as Parkinson's, or to implant a Neuralink and related devices. So remember, non-invasive outside, semi-invasive on, and invasive in. So details, a little more details. Invasive has microelectrodes directly sewn into the cortex, and you can see that in the descriptions of things like Neuralink, and they will measure the activity of a single or a few neurons. And then the semi-invasive is also called an ECOG, and I have a slide coming up, electrodes placed on the exposed surface of the brain, and they may be patterned in flexible, biologically inert materials like graphene or silk. I don't think anyone's using silk anymore, but there's materials like Kapton and graphene, both of which can be very, very thin, very conforming to the surface of the brain, and very non-immunogenic. And then non-invasive, as we've said several times, would be like EEG, MEG, which is magneto. I'm blanking on the rest of this, but using, instead of measuring electrical signals from the outside, you're measuring their associated magnetic signals. And then positron emission tomography, fMRI, and FNIR. So those are all non-invasive methods. So there's a lot of ways to get information, and I find that surprising. Actually, you would think through the bone and all these neurons that are actually, if you vision them as electrical wires, right, that are sending off a signal that you're capturing, well, they're all entwined with each other, and they're all going in different directions, and yet you can still non-invasively deconvolute this information. I think that's amazing all by itself, and that's way, way less technology than reading the neural code from electrodes placed inside the brain. So these technologies are just amazing.
I think I'm going to skip this. Oh, and here it is. By the way, I couldn't think of it a second ago. Magnetoencephalography. I just don't say it that often. Electroencephalography, magnetoencephalography, and then, as I said, functional magnetic resonance imaging. And here's all the different kinds of information that they record. But basically, EEG and MEG record very similar information. MEG is much more sensitive and concomitantly much harder to do, and fMRI encodes related similar information, but not the same. So I think this is a little too much detail, but this is how many electrodes are in a traditional EEG. And nowadays people are using much fewer, especially for specialized tasks like measuring attention. You don't need this whole cap full of electrodes. And in the old days, you may have even seen this in movies, people would place the electrodes one at a time onto the outside of the head. And now you can just pull a cap on and they're already placed. And they also used to use a conducting gel, which I believe, actually I know that modern devices don't use. And then each one of these would be a channel and you get all these different lines of data coming out. And that would be, one electrode would lead one line of data. And this is just another description of the semi-invasive. This is an older picture. Doesn't this look horrible? This is 2 millimeters. These are stiffened. It looked like those tapered bed of nails that fakirs used to entertain people by lying on them and controlling the pain. So now they take this, put it into your brain. I'm being a little amusing in my description of it, but basically it's very tiny and these electrodes are very close, which gives a lot of artifacts when this data is measured. You actually want these as far apart as possible so you don't have electrical crosstalk between them. But in any case, there's lots of different designs of Utah arrays, and this is an older one, just so that you can see what it looks like. And I think this might be the end of what I want to say in this talk. I'm going to skip this. This is a detail of a device that does a deep brain stimulation. This is a modern EEG headset that you can buy a kit for. It's called NeuroCap, and you don't get the pretty lady, but this device is actually probably from 2015. They're a couple $100, and you can just play with this at your house, or work with Brian and myself and build your own headset. And I think we'll talk about this at a future time, but a simple EEG can read, for example, your intention to put the brakes on in a car. And by reading your intention in a tense situation where time may be of the essence, if you even get the braking, if the car will brake, it senses maybe an obstruction or something, and it reads your intention to brake. It can brake faster than your foot can hit the pedal. So that does add a safety margin, even a 30-second of a second in many accidents at various speeds can provide a lot of life-saving cushions to people. So you would actually want that included in a car. This is software that can interpret that output. Remember, you could buy one of those devices and then you would need software to interpret the stream of data that comes out of it. And these are free kits. And I'm sorry that this is got some noise behind here, but in any case, this can be discussed at a different meeting or in a different video if there's enough interest. These are devices that you can buy. You can look up emotive. You can monitor engagement with a beat alert device. These are all very similar EEG devices that are already being used for marketing people, right? Are people really looking at the website, or are these ads effective? Does this dancing and paperclip annoy or enhance the experience? It's annoying. And this is officially the last slide. You can fly a helicopter with your mind. I think this is awesome. This is put out by a company called Puzzlebox. When I got this, it was $189 in stock with free shipping. And just imagine you're at work, right? You got people, you're in your cubicle or your office, you're flying this helicopter and looking at how people are reacting. I have no idea. How's there a drone in here? And you're like sending it to buzz your boss or your best friend or your enemy, and completely you've no idea where it came from. So you're freaking everybody out. I just think this is amusing, the least important and most amusing use of brain machine interface. So I'm going to end this recording and this talk with this second half. Sorry that this wasn't included at the time in the first version of this video, and looking forward to stopping this and finding where it is. I have to stop sharing. Looking forward to future meetings with you guys. I hope that you enjoyed the rest of this talk, and I will see you at the next meeting. Take care.